first I would like to thank the organizer for inviting me. So today I'll be talking about long-lived particles, some unconventional signatures, and this talk will not be very technical, so I have made some basic slides. Okay, so we all know that so far we have not found anything, and there are many possible reasons, and one of the reasons may be the following, that probably we are producing new particles, but the search methods are not very sensitive, so that we are not been able to see those particles. Okay, so or the signals are experimentally challenging. So one such possibility is long-lived particles, and yeah. So before I talk about long-lived particles, let me talk about some kind of recipe for conventional searches. Suppose you have a model, given a model. Suppose you have a new particle X and you want to search that particle. So first you will check how to produce that particle in the collider. So whether this particle can be produced singly, or whether you can produce it from the decay of some standard model or beyond standard model particles, or single production is possible. And the second one is how this particle decays to other particles, whether it decays to standard model particles or whether it creates a cascade. So this kind of questions we first ask, and at the LHC we can identify electron, muon, photon and quarks and gluons in terms of jets. Okay, and you can also identify the presence of invisible particles like neutrinos or dark matter in terms of missing transverse energy. These are actually my observables. So based on this thing, we actually classify signatures. Suppose you have a production mechanism and you know the decay mode, so you actually classify according to the production and decay modes. Like say for Higgs boson, we actually search for diphoton or 4-lepton, because Higgs boson decays to those particles. And then we actually do some kind of analysis to separate signal and background. Okay, so now say take one example, say suppose you have a particle called gluino that decays to QQ bar and a missing energy particle. This chi bar is actually dark matter. So you can pair produce this gluino. So and this gluino will produce some quarks QQ bar. So the final state will be multiple jets plus missing transverse energy. Okay, so and then you define some variables and try to find the signature of gluino. Okay, but now let's consider the possibility that for some reason, suppose this gluino is long-lived. Here long-lived means we are actually talking about LHC, so the decay length is say starting from a few millimeter to a few hundred meters. So we are talking about this kind of decay length. Okay, so I'm saying that this gluino is somehow long-lived, means this decay width is suppressed for some reason. Okay, so in that case gluino will be pair produced, but it will not decay instantaneously. It will probably travel through the detector, but gluino has some color charge, so it will hadronize and form some kind of heavy hadron called R hadron. But the point is that here, if the gluino is prompt, then the signature is multiple jets plus missing energy. But here gluino is now semi-stable, but we don't know what would be the signature, but it's no longer multiple jets plus missing it. So the point is that if the signature is different for prompt gluino and long-lived gluino. But you can ask this question so probably we are actually fine-tuning the situation and we make this gluino long-lived. Probably it's probably not possible, or it's too much fine-tuned. Okay, so let's see, in the standard model, there are many long-lived particles, and presence of long-lived particles is not really unnatural. Think about neutron, say B plus, meson, pion. There are many long-lived particles in the standard model. And there are actually several reasons. Think about the pion decay. Pion is long-lived, charge pion is long-lived because you have a heavy W boson propagator in the decay. neutron is long-lived because neutron decays to a proton, and the mass difference between neutron and proton is very small, say 1.3 MeV. That's why this decay is phase-space suppressed. This decay is actually suppressed because of the propagator, heavy propagator. And there is another example like this B plus decays to some two particles. You also have a double boson suppression, but additional suppression comes from small CKM element in the coupling. That's why B plus is also long-lived. So you have like three reasons, like one is coupling suppression, phase-space suppression, and heavy propagator. That's why like standard model particles are long-lived. We can apply the same argument for beyond standard model particles. Say, suppose you have this particle that decays to E plus, E minus and neutrino, but here this coupling is actually, it comes from R parity violation. This coupling can be arbitrarily small. So in that case, this particle will be long-lived. I have already talked about gluino. Gluino is long-lived. Think about this decay mode, like gluino decays to QQ bar chi10 through a virtual quark. If this quark is very heavy, in that case, this gluino can also be long-lived. It's actually propagator suppression. Here it's coupling suppression, and here this charge or this charged particle is long-lived because the mass difference between the charged particle and the neutral partner is very small. So in case of say some specific model, it can be as small as a few hundred MeV. So in that case, this particle is long-lived. So I am using these three arguments: small mass difference, like phase-space suppression, heavy propagator, and small coupling. So this can be applied to beyond standard model cases also. And probably we are aware of like many models called dark sector models, where you have standard model and you have a dark sector, and these two sectors are connected by some kind of mediators called portals. So if this mediator is say gauge boson, we call it dark photon. You can have dark scalar, you can have scalar portals or neutrino portals. And you can also think of some other higher dimensional operators like axion-like particles and many other things. But the point is that here this portal couplings, this epsilon or kappa or y, can be very small. In that case, these mediator particles can be long-lived. Okay, so what I am trying to say is that in many beyond standard model scenarios, you can naturally get long-lived particles. It's not really unnatural. Okay, so now, let's talk about the simplest scenario. Say you have a particle X that decays to standard model particles, and you have a coupling lambda which is small. That's why this X is long-lived. Now, so we can actually make this coupling very small, and we can change the lifetime of this particle. So it's easy. But the problem is that this particle, suppose I want to produce this particle by using the same coupling, like standard model particle will collide and it will produce this particle X, then we are also using the same coupling in the production vertex. So in that case, the total cross section will also be suppressed by the same factor lambda square. So in that case, if you like make in this model, if you make this particle X very long-lived, in that case the production cross section will also become very small. Okay. So this is actually some kind of minimal model, but we can also have other models where this LLP can come from the decay of some standard model or beyond standard model particles, or the single production of LLP is suppressed but not the pair production. So in that case, you pair produce the LLPs and the decay will be determined by different couplings. Okay, so in that case, you can have reasonable cross section. Now, let me give you one example of LLP searches. Like here, again I am talking about strongly interacting particle, but this gluino is not long-lived particle. So we pair produce gluino, but this gluino decays to some quarks which will form jets, but to another particle which is long-lived. Gluino is prompt, but this X is long-lived. But you see that from the decay of gluino, you have some prompt jets. So you can have multiple prompt jets and you can search this scenario using multiple prompt jets and missing energy. This is possible. But the point is that we are not fully utilizing the features of this process because we are not really considering the presence of these long-lived particles. We are just focusing on prompt particles which are coming from the decay of gluino but not the LLPs. So in reality this will happen, right? So in addition to those prompt jets, you will always have this charged long-lived particle and that will travel, and in this situation that it will travel up to some finite point and then it will decay to probably some dark matter and some soft particles. So this is actually something called disappearing charge track signal, because you will see this track up to some point and then you won't be able to detect those particles, so this particle will disappear. Okay, so this is a classic signature of long-lived particles. So probably you can say that, okay, so let's search this process using multiple jets plus 2 disappearing charge tracks, because we have this thing in the final state. So I just want to show one example that, see, let's not go into the detail, but see this is actually this charged particle and this is the gluino mass. So just consider these two lines. One is this line, this blue line, which actually is the limit on the parameter space where we have not considered the presence of long-lived particles, and then the limit is stronger and this limit is weaker where we have actually considered the presence of these disappearing tracks. So we have taken additional information, but still the limit is much weaker than the prompt search. The reason is the following, that in this analysis, the Atlas collaboration, they are actually, the question is how to identify that disappearing track, and they assume that the length of this disappearing track should be at least 50 centimeter, but the typical decay length of this particle is 5 centimeter. So you will always have, we have only a small amount of events where this particle will propagate up to 50 centimeter. So we are actually losing events because of this kind of strong conditions. So in that paper we actually considered other possibilities, that we should probably try to construct shorter tracks, and nowadays actually like both CMS and Atlas collaborations have done major improvements in their analysis, and they are now talking about tracklets, means shorter tracks, shorter disappearing tracks. Okay, and this is another example. So here you produce this long-lived particles phi that decays to BV bar. Okay, now see, consider this line. This is actually some kind of exclusion limit. Consider this black line. So here you see this is actually the limit for prompt search. So the point is that you see, as we increase the decay length of this particle, the limits are actually become stronger, and then suddenly it becomes weaker. Okay, the reason is the following, that in the final state you have B quarks, or that will form B jets, and when we search for B jets, there we actually search for some kind of some kind of secondary partices, some kind of long-lived particles in the final state. So because of this phi, which is slightly displaced, you will be able to identify those B jets more efficiently. That's why the limit becomes better. But after some time, if this phi is highly displaced, then you won't be able to identify those B jets, and then the limit will become weaker. Okay, so what I am trying to say is that, so you can actually search long-lived particles using existing prompt search analysis, but that won't be efficient. So you need some kind of dedicated analysis in order to search these scenarios. Okay, so I will just talk about a few unusual features of LLPs. One is, suppose let's consider this scenario. This you have produced this X, and X decays to E plus E minus. Okay, and think about prompt scenario where you produce X and that decays to E plus E minus. So what would be the signature? What is the definition of an electron at say at some experiment, say CMS? So the definition of electron is the following, that you will have a track in the tracker and you should have energy deposition in the electromagnetic calorimeter, and you should not have any energy deposition in the hadronic calorimeter. So if this particle X quickly decays inside the tracker, that's the first part of the detector, you will observe these two electrons and you will be able to identify this particle X without any problem. But now this is LLP, so there is a chance that this LLP will travel up to some point and it will decay to A plus A minus. There is a chance that if the LLP travels like a few centimeters, then this electron, this track reconstruction algorithm may not work, and in that case you may not be able to identify those tracks coming from electron, but you will be able to see the energy deposition in the electromagnetic calorimeter. Okay, so but that's how we identify photon in the experiment. You should not have any tracks in the tracker, but you should have energy deposition in the electromagnetic calorimeter. So this LLP decays to E plus E minus, but it looks like a photon. Okay. The third option is that this LLP travels further and it decays inside the hadron calorimeter. Okay. So in that case, there is no track in the electromagnetic calorimeter, there is nothing, no energy deposition in the electromagnetic calorimeter, and you have energy deposition in the hadronic calorimeter. So this means that it will look like a neutral hadron. Again, it decays to E plus E minus, still it looks like a neutral hadron. And the last one is like this LLP travels, it passes through all the detector part and it decays outside. So in that case, it will look like some kind of invisible particle. Okay. So what I am trying to say is that for prompt particle, we actually, if we know the decay product, that is sufficient to define the final state. Here, it not only depends on the decay products, but also the lifetime of the particle, where it decays. So depending on the position of the decay vertex or decay position, you will see different final state. That's why it's actually more challenging, and you need some kind of dedicated algorithm to identify those situations. That's why it's actually, you have added another dimension, which is the lifetime. Okay. Okay, so there is another strange feature of LLP. The point is that it's the following. So suppose this is one calorimeter cell and this is the interaction point. So if one particle hits that calorimeter cell, and we know this angle with respect to the z-axis is 30 degree, then we will say that this calorimeter cell represents theta equal to 30 degree. And this calorimeter cell is 20 degree, because if some particle starts from this point and hits that particle, then the angle with respect to the z-axis will be 20 degree. So that's how we actually align the calorimeter in terms of pseudo rapidity. Okay. But for long-lived particle, consider this long-lived particle, it goes like this and then it decays to two particles, and this particle hits the same calorimeter cell. Okay. So what do you tell about this particle? You will say that, oh, this particle is coming from the primary vertex with angle 30 degree. But it actually, probably the angle is different, because it comes from this point and it moves like this, because it travels up to this point. So this will actually create some kind of non-trivial effect on the analysis, and this kind of effect you won't be able to see if you do some kind of fast simulation, because layered segmentation and all these things are not there in the fast simulation packages. So you won't be able to see that. Okay. So this is actually non-pointing thing. So one example is the following. Suppose you have a Z boson that decays to two quarks, and I place this one quark here, and then another quark will move in a circle, right? So this is the second quark. If we actually specify the energy of this particle, then the angle is fixed. Okay. So this is the first quark and this is the second quark. It's actually jet. So in that case, if you actually average over multiple jet images, it will look like this. But if this Z boson is displaced, then this nice structure will be lost, and you see that there are actually multiple effects, and you won't be able to see this nice kind of this gap between two jets because of this misalignment. Okay, and there will be other effects like the physical area taken by the decay products would be smaller and smaller, and it will depend on the decay length. So this feature will be lost. And the machine learning can actually, some kind of image recognition can identify this kind of strange jet events. Okay. And there is another like strange feature which is like this is actually non-pointing nature, but in some cases the decay products of the long-lived particles can also come back, like it can move in the backward direction. If the long-lived particle is heavy, it can also, like suppose this gluino is like moving in that direction, but some of the decay products can also move back to the in the backward direction. Okay. So then so I just want to tell you that the question is, how do you actually identify the signatures of long-lived particles? Again, let's consider this example that phi, you produce this long-lived particle that decays to E plus E minus. So you start from this point, this LLP, it goes slowly and it reaches here and it decays to two particles. Okay, and then the decay product hits this calorimeter cell, and suppose you know how to measure the time. Okay, suppose you know where it starts T0 and you know T1. And this LLP moves slowly because it's heavy LLP. In that case, you can actually calculate the time difference T1 minus T0, and you check this time difference with respect to some prompt particle that starts from here and hits here. So this time delay would be more for long-lived particles. Okay, so in principle, you should be able to identify the time delay, and in like experiments, there are some parts like electromagnetic calorimeter, and in future MTD will be there, so which can measure the precise timing of these particles, and from there you can actually construct multiple variables, and you can separate long-lived, like the signature of long-lived particles from prompt particles. But I want to show you one. This is actually some kind of like timing variable. It's some kind of energy weighted timing variable for jet, and you see this is the distribution. So, but if you see that there is actually red line which is coming from QCD jet, so-called prompt particles, standard model background, and this blue line is actually from some long-lived particle scenarios where the mass of this particle is 30 GeV, but the decay length is 10 centimeter, and this is another LLP scenario where the decay length is 100 centimeter. You see that if the decay length is 100 centimeter, you can separate signal and background easily. But if the decay length is 10 centimeter, it's not very different from QCD jet. But I already told you that probably in the standard model, all these particles are prompt, it should reach fast, right? But it's not true because of this QCD. QCD has a long tail, this distribution, and the QCD cross section is huge. And there are various effects actually, like the intrinsic spread of the beam spot in the temporal and longitudinal direction. You have some long-lived particles in the standard model also, like K-short and many other particles that can also create some kind of time difference and the resolution of the detector. Okay. So in some cases, you will be able to use this information, like timing kind of information. The another option is that suppose see this thing that this LLP decays here and it creates some charged particles. So if you can identify those charged particles, you can actually try to get this point which is called secondary vertex. And this is your standard model background. All these particles are coming from the primary vertex. Here you have a secondary vertex far from the primary vertex. If you can identify this point, then you should be able to like remove all the standard model background theoretically, right? But again, it's not fully true because you are searching for this kind of scenarios where you have a point and multiple particles are coming out. But there are other like instrumental backgrounds like this one. So suppose one hadron, that hadron hits some part of the detector and it produces secondary particles. So in that case, it will look like a secondary vortex. Or suppose you have like some charged particles, the charged tracks, and you have some kind of, because of the reconstructions, you have some kind of accidental crossing, and this point will look like a secondary vortex. So you really need to know the full material map in order to suppress all those backgrounds. And even this material V2 map is not enough. You have to apply some cuts, like the invariant mass of the vortex and the track multiplicity. If the number of tracks is high and if the invariant mass is high, then you can reject all those backgrounds. But if the mass of this LLP is small and if the number of particles coming from the secondary vortex is small, then it's actually very challenging. Okay. And this kind of situation is very difficult to study in case of, say, at LHC, unless it decays to muons. So in such cases, like you have light LLPs and which decays to say E plus E minus, and the mass is say 1 GeV. In such cases, you can use different like dedicated detectors like phasor, which is actually this LLPs can get boost, longitudinal boost from the decay of mesons, and we already have one detector in place called phasor detector, which is 480 meter from the primary vertex. So that can be sensitive to this kind of light long-lived particles below 1 GeV. Okay. And you can also think of some kind of fixed target or beam down experiment which are also sensitive. Okay. And if you have like transverse detector, it can actually complement CMS results, and one such detector is called Mathusla, which is a proposed transverse detector. So like you need multiple dedicated detectors to identify various signatures of LLPs, and I'll just talk about only one, in last 1 minute I'll just talk about one point, which is actually the following, that LHC is not built for long-lived particles because they actually thought that new physics would be prompt. So then now actually they are modifying their techniques and all these things, but initially it was not built for long-lived particles. But for future colliders, we have this option, right? So we can think ahead and we can design the future colliders in such a way that you have a place for dedicated detectors. Okay, so we have done some analysis. We have done some work in this direction. We actually proposed two detectors, one in the transverse detector and another one is the forward direction. So we are actually working in this direction, and there are actually many things to do in that for future colliders, and I just want to thank my collaborators, like two students, Ritoja and Prabhat, who have actually done work in this direction extensively. And we actually try to analyze a few things like the dedicated trigger developments for long-lived particles using like timing variables and energy deposition, muon spectrometer. We are actually trying to explore various options, and we also use machine learning in order to see this kind of strange signatures. Okay, so this is the summary. So for LLPs actually are really motivated, well-motivated theory. You can find it in many BSM scenarios. Signature not only depends on the decay products, but also depends where it decays, the lifetime. And many unusual signatures are possible, and you need like some kind of good knowledge of detector in order to estimate the backgrounds. And you need dedicated detectors to probe light LLPs. And I think for future colliders, we should think about dedicated detectors so that we can optimize we can cover all the possibilities. Okay, thank you.
Questions?
I just have a very naive thing to ask. In your time analysis, that slide which you are showing about the timing, how do you know how long you should keep this time open, the gate open, let's say, once you have, what motivates that? Yeah, here, let's say.
Yeah.
What motivates to keep that, how long you should keep that open?
Okay, so I think they actually apply some cut of around 20 nanosecond. Okay. So if the LLP reaches after that,
So you're expecting that your LLPs will be all within that.
yes,
Like,
yes.
okay.
So there are these exotic candidates in the charm and the bottom regime, where theoretically there are many predictions for long-lived states, bound states, as per strong interaction. Bound states as per strong interaction, so they can only decay weakly or otherwise.
Okay.
So these kind of signatures in the tail can we also apply for such states, and also if you say that dedicated experiments are needed for such states, we need dedicated experiments for each of such states. It actually is varied over 3 to some 10 G.
So it depends on it depends on the lifetime and the decay product of those particles. So if you specify those things, then like, yeah,
It is virtual data called PC.
So there is this tetraquark BC UD, U bar D bar,
okay,
which we claim that will be like 40 MeV bound, for example,
okay,
and it can decay only weakly.
okay. So the point is that if it decays within some, the problem is that what would be the background and what's the decay product? If it decays to muons or something, if you have like muons, I think we'll be able to, I think we can ask Kajoridi also, like, because you are also doing this kind of analysis, right? B2S gamma or so for, if you have muons, I think you have a chance. And if it is like only some hadrons, and if it is displaced by a few millimeter or something, then I think it would be very difficult. That's what I guess.